So good morning again. I am Claudio Guarnaccia, Associate Professor of Applied Physics in the Civil Engineering Department of University of Salerno. In this second presentation, I will present work performed in my lab about road traffic noise modeling. And in particular, we recently developed a model that is calibrated on computed data set. So in this presentation, I will present some analysis about parameter sensitivity results of this model during the calibration. So this is the summary of my presentation. I will just briefly present the motivation and the goals of the paper, the research objectives, the materials and methods, and the results. The framework in which we move is the problem of road traffic noise, and it has been estimated that 20% of European Union population is exposed to high level of noise, in particular to daily levels. This LDEN parameter is daily, day, evening, night, that are greater than 55 dBA. That is the threshold that is usually considered to be the starting of annoyance and of health problems. I will go fast on this. Urban areas are the most affected zones, and in particular, road traffic noise is the main source in both in urban areas and outside. And it is, of course, everybody has a road that comes to his place, but maybe railways are less. Railways, airports, and industry are usually not mixed in urban and in residential areas. So the motivations of this study concern the development of a road traffic noise model that can be used in any conditions. In fact, when we have to deal with the problems of road traffic noise, we can do measurements. Of course, this is probably the best approach to have field data, real data, or we can do with simulation. In this case, we need to calibrate a formula to calibrate a model and then to validate on field data. And usually calibration is based on real measured data. But when we do this, we somehow introduce a bias in the model because the model will be site dependent. In fact, if we calibrate on, for instance, site 1 data, of course, if the validation is fine on this site, it means that the model works. But this does not mean that the same model can be easily applied in another site. Think, for instance, the statistical models that have been developed in the 50s, such as Burch from Australia or Cort in UK. They are validated, calibrated on data collected in these nations. But if we want to apply the same model, I don't know, for instance, in US or in India or in another country, we have to take into account that there are different fleets, different vehicles typology, different maintenance duties, different speed limits. So it is not sure that the same model can be applied in another place. So our idea was to compute a data set using a simple analytical model to mimic and depict a large variety of situations, of conditions, and then to calibrate the model on this computed data set. So today I will present some studies about these 4 items about the database. So sensitivity analysis about numerosity of data, different sets of data, and the effect on computational time and the presence of outliers. So the computational part of the database has been run considering these variables on the left: traffic flow, the speeds of the categories, the percentage of medium and heavy vehicles, and the distance source receiver. And all these variables have been computed starting from the flow with steps between 10 and 200 vehicles per time. The steps are 10 by 10. And then for each step, we have a random extraction of the other variables according to flat probability distribution in order to do not include bias in the model. Just to say, if a flat distribution means that we are simulating, looking at the speed, we are simulating with the same probability both urban areas in which we have lower speeds or highways or extra urban. So this is the reason why we choose flat uniform probability distributions. As I mentioned, for each step of the flow, then we simulate this, and the step can be repeated n times, and this is one of the variables that we checked in this study. And this in this slide is even more clear that for each step we have repeated once, twice, 5 times, and etc., resulting in overall numerosity of this data. Of these rows, because each row has a value for each independent variables. And then this has been also repeated 100 times using different seeds in order to also check the robustness according to the random distribution. And the equivalent noise equivalent level, LEC, over time has been simulated using, actually the approach is modular. So we have a model that simulates the emission of each vehicle or each single vehicle. In this application, we use the US REML model, but it can be changed according to the country in which you want to test, or in any, we also plan to make tests on this, changing the noise emission model, for instance, using the Knossos model, that is the reference model in Europe, or other models. And then the computation, the propagation has been computed using the simple point-like source approximation. And finally, we calculate the sound exposure levels of each category of vehicles, light, medium, and heavy vehicles, according to the formulas here. Once we do that, we can combine the three contributions from light, medium, and heavy vehicles in a log sum, and then we can also normalize, because the cells are calculated on 1 second basis. We can normalize according to the time that we want to analyze. It can be 1 minute, can be 15 minutes, can be 1 hour, as usually is done in road traffic noise monitoring or whatever. And once we do this, we have a vector of equivalent noise levels that can be used to run a multilinear regression that was subject of the previous paper that I mentioned, in order then to analyze the residuals and to make the sensitivity analysis, checking the residuals. And we just used the mean value, the standard deviation of the residual distributions. We checked also skewness and kurtosis and the Shapiro-Wilk normality test. In order to check the influence of outliers in this calibration, we also test a trimming of the data, removing the data that produce the higher residuals, let's say the outliers in the residual distribution. This can be seen like a kind of overfitting procedure, but it is not, because the idea is that when we produce the calibration data set, as I mentioned, we are simulating different conditions. For instance, with 10 vehicles per hour, we can also get a speed that is usually associated with the traffic jam. But of course, with 10 vehicles per hour, you do not have traffic jam. So the idea is that the outliers of these residuals are obtained because in the computation of the data calibration data set, we were too wide somehow. So we included conditions that are not really real somehow. And so we introduced this K0 parameter multiplied for the interquartile range. And we also check the improvement of the residuals changing this K0 parameter. Going to the results, I'm going fast, try to be in the 15 minutes slot. So the first results are the distributions of the residuals according to the increasing of the data set. So that's why the distribution raises, and we have a table with statistics of the residuals. The mean is basically, let me also underline that is very common and it is recommended in road traffic noise, but in any, uh, when dealing with sound levels, to do not go farther than one digit after the comma, because these are log results, and the better the higher resolution of any instrument, a class 1 resolution is usually 0.1. That's why usually the results are given with one digit after the comma. But for some computation, we left more digits in order to appreciate the changing according to the parameters. So for instance, the standard deviation is given with 3 digits, and we see a slight reduction, increasing the data that is somehow expected. And also the results changing the seed. So with the 100 repetitions, produce a substantial reduction in the standard deviation of most all of the of the of the sorry, of the parameters that we are presenting. So you can see that from z, the reference seed that is equal to 0 is somehow similar in terms of mean values of each statistics, but the standard deviation, the range, is decreased. You can see here plus minus 0.069 goes to reduces of one order of magnitude, and this is common for mostly all the statistics that we are presenting. According to the trimming of the outliers, we found a minimum for 0.2 for k0 equal to 0.1 in terms of mean. Well, the mean is always 0, but the standard deviation is the minimum for this 0.1 trimming. And also the other statistics are confirmed. This is the same analysis, but also including the dataset size, and basically what I showed here is for 1 times of repetition, and so these results are in this column, this row. And so you can also see what happened when we increase the calibration dataset size, increasing slightly the statistics. So the idea is that we basically gave a quantitative results about sensitivity analysis of these parameters. About the computational time, we plot both the wall time and CPU time. Wall time including also other process ongoing on the machine, and we found let's say an increase starting from 10 times of repetition, and so one can check which is the optimum point according to the time available, and also according to the level of reference of that one wants to achieve. So in conclusions, we found that the size of the dataset, well, actually does not greatly affect the residuals, just a slight, you remember, a slight reduction in the standard deviation. The outliers removal, trimming, gave some results and led to similar values of the mean of the residuals, but with a narrow distribution in this case. And also the combination of increasing of the size and outlier removals improved the results. The random generation did not really affect the independent variables, and that's it. So I stop.